Hello everyone and welcome. My name is Jason Gregerson. In this video we're going to be talking about reduction of order and how we're going to use it to find the second solution to a differential equation given a known first solution. We're going to start by looking at the general reduction of order process. So consider a differential equation like this. Here we have the differential equation x double prime plus 3 over t times x prime equals t. And the idea of reduction of order is we're going to be able to take the second order differential equation and reduce it to a first order differential equation, which will be easier to solve. So in this problem, what we notice, the key idea, is that there is no x term. There is no just x term. We have x double prime and x prime, but no x term. So in that case, our process is to let w equal x prime. If w is equal to x prime, that means that w prime would be the derivative of w, the derivative of x prime, which is x double prime. So if we choose to let w x prime, then w prime would equal xw, x double prime. And as we plug these values into our differential equation, x double prime would be w prime plus 3 over t times w equals t. And so by making that appropriate substitution, we've now reduced the order of the differential equation to a first order differential equation. And from here, we can go ahead and solve the differential equation. So in this specific example, I see that I have a first order linear differential equation, which means I can identify my integrating factor, which should be e raised to the integral of 3 over t dt. I can pull out my factor of 3, integrate 1 over t to get the natural log of the absolute value of t. From here I can bring my factor in as an exponent and take e to the natural log to simplify this to t cubed. So there's my integrating factor. From there, I will say that the derivative with respect to t of my dependent variable times my integrating factor is equal to my right-hand side times my integrating factor, so that's t to the fourth. I'll integrate both sides to get w times t cubed is equal to t to the fifth over 5 plus some constant, and I'll generate my final solution, which is w equal to t squared over 5 plus c times t to the negative 3 power. All right, so this is my solution to that first order differential equation. Now I have the value for w, and now step 2 is to calculate my missing value of x that I was trying to find. X is really equal to the integral of w with respect to t. Once again, since w is x prime, x must be equal to the integral of w. And so now I can integrate my solution, t squared over 5 plus some constant, t to the negative 3 power. And when I integrate this, I will get t cubed over 15 plus t to the negative 2 power over negative 2 times my constant here, plus some new constant, call it C2, call this first constant C1, and this is my expression for x. Now, I could do some further simplification of constants, but the idea here is that I have x as a function of t with two arbitrary constants, which is what I would expect for a solution to a second order differential equation. So reduction of order took the second order differential equation, I made a substitution to reduce it to a first order, I was then able to solve it, and then go back and integrate to find my original value x. That is the concept of reduction of order. Now where are we going to use this idea? We're going to use this to find the second solution given a known first solution. So consider this differential equation. Here I have t times x double prime minus the quantity t plus 1 times x prime plus x equals 0. Right, so this is a second order linear differential equation that is homogeneous because the right-hand side is equal to 0. That means that the solutions to this differential equation form a two-dimensional vector space. So my goal is to find two linearly independent solutions, x1 and x2, and then I can write my general solution as shown in step 5 here as a linear combination of my basis vectors for this solution space. Now sometimes I might not know two linearly independent solutions but only have one. If I know one solution is x sub 1 equals e to the t, how can I find a second solution, which probably shouldn't be shown there? How do I find my x sub 2? In this process, I start by saying, well, let x2 equal some unknown function times x1. And the thought process here might be that, well, my second solution could not be a constant times x1, because then it wouldn't be linearly independent with my first solution, so maybe it's a function times x1. So in this specific case, I'm going to assume that x2 is equal to some function u times my first solution. And then I'm going to take the derivative, take the second derivative of my guess at x2, plug them into my differential equation, and try to solve for my missing function u. Once I know u, I'll know my second solution is u times et. All right, so I'm going to have to calculate x2 prime. Well, u is a function of t, and e to the t is a function of t, so I have to use the product rule. So here I'm going to get u prime, the derivative of the first, times the second, plus the first times the derivative of the second. That's my x2 prime. Then I'll have to calculate the second derivative. Well, this is going to be the derivative of this product plus the derivative of this product. The derivative of the first product is derivative of the first thing times the second plus the first times the derivative of the second. I move on to the second term here. So plus the derivative of the first times the second plus the first times the derivative of the second. And then I can consolidate my two middle terms to get 2 times u prime e to the t. So we'll just consolidate these to look like that. Our next step is to plug all these values into our differential equation. My differential equation up here says take t times x2 double prime. That's t times u double prime e to the t plus 2t u prime e to the t plus t times u e to the t. I'm taking all of x2 double prime times t. Then I have to take minus the quantity t plus 1 times x prime. X prime is this guy right here, u prime e to the t plus u e to the t. And then lastly, in my differential equation, I have plus x, but x is u e to the t. And all this stuff is supposed to be equal to 0. So I've made an assumption for x2, calculated all the derivatives, plugged it all into my differential equation, and now I have a big, ugly substitution process. So to do that, I'm going to have to clean some stuff up first here. So I'm going to reorganize a couple pieces, rewriting some of my first pieces, plus 2t u prime e to the t, tu e to the t. Now to kind of organize all this, I'm going to take t plus 1 times all that stuff, so that's t times everything. That will give me t u prime e to the t plus t u e to the t plus 1 times everything, so that's plus u prime e to the t plus u e to the t. And then all that stuff times negative, so negative, 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 negative as I distribute that negative sign, plus my last u e to the t. So a lot of tedious work here. Now when we're all through that stage, I'm going to start gathering up my like terms. So I'm going to highlight all of the terms that have just a u in it. Here is a u term, a u term, a u term, and a u term. And if I consolidate all these, I'll see that minus u e to the t plus u e to the t is equal to 0. And I'll say t u e to the t minus t u e to the t is also equal to 0. All those terms will cancel out. And that's an important simplification. Now I'm left with my u double prime terms. So I'm going to organize those. I'll write u double prime t e to the t. I'm going to consolidate all my u prime terms. Here's a u prime term, here's a u prime term, and here is my last u prime term. So the first two have a t with them. So if I take 2t u prime e to the t and subtract 1 t u prime e to the t, the result will be plus t u prime e to the t. And then I have minus u prime e to the t all equal to 0. These two terms have a u prime, so I can simplify this to u double prime t to the t plus u prime t e to the t minus e to the t equals 0. Okay, all of that work has led us to this stage, and this stage, no matter what our differential equation was, will have one common feature. That common feature is there will be no u terms. All that algebra leads us to this phase, which has prepared us for our reduction of order. From this stage, I can go on to step 3, and I can let w equal u prime, which means that w prime is equal to u double prime, which is going to let me reduce this second order differential equation in u to a first order differential equation in w. So plugging these values in, I'm going to get w prime t e to the t plus w, all this other stuff. This is a first order differential equation, and it turns out I can solve this with probably separation of variables. Now we're going to skip ahead a little bit, and so the idea is if you went through this process and solved this with separation of variables, we would find out that our w would actually equal e to the negative t times some constant. I'm going to call it c sub 1. So once again, big step here. This is a big step of separation of variables for a first order differential equation, right? And you can work that out on your own. But having solved that, I now know a value for w. But my original goal was to find u. So to find u, I need to integrate. To find u, I need to integrate my value of w with respect to t. So that will be the integral of constant times t e to the negative t with respect to t. So I'll pull my constant out front, and I'm integrating this. Once again, we're going to skip a little bit of work here, which you can verify in your own time, but we'll do this integration by parts. And it's a pretty straightforward integration by parts problem. And when we do that, we'll get our value of u, which will equal to some constant times the quantity, negative e to the negative t minus t e to the negative t. All right? Now, we don't really need this constant because really the reason we're looking for u is if we look up at step 1, we're trying to find our second solution, which is some function times x1. And then in the end, our final general solution will have these constants c1 and c2. Those will all be consolidated with this constant. So we can drop out our general constant c. So this means that our x2 value is really u times x1. Remember, x1 was our original e to the t. So when I take u, which is now negative e to the negative t minus t e to the negative t, all that stuff, multiplied by e to the t, the result is going to be negative 1 minus t. And this should be my second solution to the differential equation. All right, so that is checking our box for number 4 here, forming our second solution. And then lastly, our general solution will be a linear combination of our first two solutions. That'll be our general solution. So once again, the general steps assume a second solution is x2 equals some function times our first solution. From there, we calculate the derivatives and plug it into the differential equation. This will always eliminate the u terms. At that point, we can then go on to step 3, make our substitution w equals u prime. This will reduce it to a first order differential equation w, which we can solve. We solve for w, and then integrate w to find u, allowing us to finally form our second solution, and then lastly, we form our general solution. All right, big, long, ugly process. We're going to simplify that in class, but for now, that is the process of reduction of order. And thanks for watching this video.